In this video, we're going to go through the alternative methods of extracting metals, and we're going to talk about a lot of exam-style questions and answers, so it's a really good one to do. Now, we're going to use copper as the example, but let's start off with ores themselves. So normally we talk about extraction of two types of ores, and we talk about really aluminium oxide and hematite. We extract this through electrolysis, which is in unit 4, and we extract this through addition of copper, which is also unit 4. So please, if you're not sure about those, go back to those kind of videos. Now, ores are just metal-based compounds that are mined from rocks, take a lot of energy to extract, but it's worth the money to do so they can make money out. Simply put, they make loads of money. Okay, now we're talking about low-grade ores in this video, which is where you couldn't normally mine them in the way you do. But why do we actually have to look for these low-grade ores, right? It's because there are limited resources. So there's limited resources in the world, and basically we need to start looking after it a lot better. So many ores are becoming scarce or limited, okay, and we need to find new sources. So an example of this is your mobile phones. Now, a lot of you probably have mobile phones that you keep in a drawer somewhere, and if they're old, you don't recycle them. Well, please recycle them, because the touch screen technology is made of indium oxide, and indium oxide is becoming scarcer, and therefore we must recycle, because all we have to do is take that mobile phone, take it apart, take the indium oxide out, and then make a new one out of it. So recycling, really important in a modern day with those mobile phones. Now, if we look at copper precisely, and why do we do that? Well, copper is becoming more limited, okay, and around 40 k's or kilograms of copper is used in an electric battery for a car, for example, like this Tesla that you've got here. Now, if that's the key, and electric cars are increasing in number around the world, best-selling car in the world was an electric car last year, okay, it's really important that we conserve that copper. Now, copper is also used in home for our pipework, especially in Europe. You'll see a lot of pipework made out of copper. Now, we must find new sources and develop ways of extraction from the low-grade ores. So the low-grade ores. So high-grade ores are your bauxite, your aluminium, and your iron oxide, hematite. But low-grade ores, ones with a smaller amount of copper, for example, or metal, that's not economical to extract. Okay, so it's uneconomical to extract using a normal method. So we're going to develop new methods, and we're also going to recycle. So this is the point now. Why must you recycle? And these are the exam-style questions. Well, first of all, you have to conserve those copper ores. They're finite, they run out. So really key term is to use the word finite in your exam questions. It reduces waste and uses less energy. Now, lots of energy is used to mine different ores. If we don't have to mine them, we can do it in a different way. We will save a lot of energy and fossil fuels. It reduces the use of landfill. So we're not throwing away things into a hole and leaving them for hundreds and hundreds of years to break down. And also it reduces mining and quarrying. So mining and quarrying, big holes in the ground, cause a lot of environmental impact. And so it reduces that mining and quarrying because we don't have to, because we can do it in a different way. So the question is, what are the different ways? And the first way we're going to talk about is phytomining. So phytomining, light and mining really, is just the idea that you're going to grow plants in low-grade copper ore. Now again, all of it in green means you have to put it in that exam answer. So make sure you say that those plants are growing in the low-grade copper ore. And that absorbs the copper. And they do it with grasses, like you can see over here. Then they cut them down and they harvest them, and then they dry them and burn them. Really important that you say that they burn. And that contains the metal compounds. And those metal compounds can be oxidized. And we'll go through a form of oxidized metal that you can then extract. And I'll show you how to do it. I'll also show you what happens when you dissolve it in the acid. So basically you burned the ash and then you dissolved it in the acid. And I'll show you a reaction for that as well. Last stage is to electrolyze, to produce the copper, or use displacement of the copper by adding scrap iron. So we're going to show you those examples now. So there's three things we're going to show you. We're going to show you what is the reaction when it dissolves in acid, what happens when you electrolyze it, and what happens with displacement in copper. So let's put that to the side and then have a look at what we're doing. So think about it. We've got the ash. Okay, and inside the ash it's burnt material. So it stands to reason that the copper that's inside of there would be oxidized. So I'm going to give you the formula, and I'm sure they would give you the formula in the exam if they did this. That copper oxide is a solid, and then you add it to an acid. So I'm going to add it to H2SO4. And again, that's an acid, so it's aqueous. And then when I bond that, okay, what's going to happen? You've got metal oxide plus an acid. Metal oxide plus acid goes to salt plus water, which is unit 4. Now the salt is from the acid. The acid itself is sulfuric, so it gives you a salt of sulfate. So we've got copper 2 plus and SO4 2 minus, and you need to remember that SO4 is 2 minus, but you can also work it out from the fact that H is plus, and there's 2 of them, so if 2 pluses, and then sulfate must be 2 minus. Now they cancel out, so your formula of your salt is going to be copper sulfate. That's aqueous. We've done this in blue for a reason, because copper sulfate is blue. And there you have it, and there's your equation happening when you take the ash, you put acid in it, and you get copper sulfate. Now let's imagine if then we do the next one, because this is our stage here, ash dissolved in acid. And then we say, right, we'll do electrolysis next, but let's look at displacement of the copper from that solution that you've got. So you've got copper sulfate, and you've got a copper sulfate solution here like that. So you've got a copper sulfate solution. That's the copper sulfate that you made in the, with the ash dissolving in the acid. And then what you're going to do is you're going to add to it your scrap iron. Your scrap iron is going to be just iron. Okay, so Fe solid. Now, this, okay, is more reactive, okay, than copper. Okay, so that's more reactive than copper, which means it displaces the copper. Okay, so it displaces the copper. So that means that Fe is going to swap with the copper, and that copper is going to be kicked out. Okay, and then what you're going to have is your purple FeSO4, and that's aqueous. So we've got here, we've managed to purify or extract the copper, because it's nice and solid now, and we can use it to make our pipes and make our batteries. Okay, because that is a liquid, so it's nicely separated, and we've done that using scrap iron. Let me put that above here. Okay, so this is your scrap iron. So your salt, copper sulfate, plus your scrap iron. Then you get a displacement reaction because the iron is more reactive than the copper, giving you copper plus your iron sulfate. So this is this stage here, which is the top, and then displacement of the copper is here. And that's the 2 equations you may well be asked in the exam. So we have gone over what happens when you add an acid to the ash and what reaction you might get, and the displacement of the copper. But now we're going to do the electrolysis. So here's a simple electrolysis setup. Power pack, electrodes, stick it in the solution. This time it's copper sulfate solution because we want to extract the copper, and that's what was made when the ash was dissolved in the acid. Right, okay, so I want you to look carefully at this. Inside there is copper and sulfate, but there's also water. We'll talk about that in a bit, but there's copper and sulfate. Right, look at these 2 electrodes and tell me what happens. Okay, there you go, right. So, if we look in here, we've got orange-brown and bubbles. You also noticed up here, my water has appeared. Okay, so what do you think is happening, taking into account there's water in there? That's got orange-brown, that's got bubbles. Okay, so stop the video and try and do it. Now, if we're doing this, negative and positive electrode, that's the first thing is. Now the cathode is the negative electrode, okay, and the anode is the positive electrode. I don't like the terms anode and cathode because sometimes they can get very confused, so I think it's simpler to keep your mind on negative and positive. Now, if you look at the negative, you can see that it went from grey to orange-brown. Orange-brown suggests you make copper. Okay, and if that's the case, and there's copper 2 plus floating around, it makes sense that the 2 plus would be attracted to the negative electrode. It's negative here, 2 plus is floating around, this 2 plus goes towards the negative electrode, there gains 2 electrons, turns back into copper, and you've got your nice orange-brown. Remember, there is a rule, and the rule is if in electrolysis the metal is more reactive than hydrogen is produced, but if it's less reactive than hydrogen, it is produced, right? So the only metal in the reactivity series that's less reactive than hydrogen that you know is copper. So always remember when you put in copper in electrolysis, that's what you're producing. Okay? Now, if we then move on to the next section, notice the water's split. Now if the water splits, that's because I'm putting electricity into it. And that electricity just chops it in two. Okay? And this is what happens at the anode, the positive electrode. So remember, if the solution is aqueous, this is another rule from a different unit, and it contains an X halide, X minus, which could be Cl minus, Br minus, etc. Okay, the halogen is produced, X2. So these bubbles would be the halogen. But did we have a halide? No, we didn't have a halide. Okay, otherwise oxygen gas is produced. And you might ask, where does that oxygen gas come from? Well, it comes from the water that when you put the electricity through, splits into OH minus and H plus. And that OH minus then creates this gas, and that gas there is oxygen. Okay, and unfortunately, for many of my students who don't really enjoy this part, you must memorize this equation. So if it's in green, you must memorize this equation. So what I'd suggest you do is, for electrolysis, following this rule. So when it's not a halide, it's this equation. So you need to remember it. So put it on a card, put it on your wall, and try to take it in through diffusion, osmosis, whatever you want to call it, off the wall into your brain. Okay, and just leave it there so you're walking past it every single day. Okay, but you must remember it. And that is how you do copper electrolysis after you get a solution from phytomining. So the next part is to discuss the advantages and the disadvantages. Now, first of all, advantages are no large amounts of rock to be mined. Remember, you are just growing plants. You are not digging up loads and loads of soil or anything like that. So no larger rocks, no large amounts of rocks to be mined. Now, less fossil fuels burnt. Remember, when we're doing the large amounts of rocks, we are using excavators which use a lot of fossil fuels. And so if we're not doing that to the same amount, less fossil fuels burnt in the process. Now, disadvantages. It takes a long time. It's a plant. It takes a long time to grow a plant. Okay, so that's not good in terms of money. It takes more time and therefore costs the company more money. High-grade ores are still available. So, obviously there must be, otherwise we wouldn't be producing all of these electric cars. And the land may not be available to use, or you may not have found it. So, if that's the case, they're all green. And that is a clear answer that may come out, okay, in your exam. So make sure you analyse these steps and try and think of what are the best and the worst things about it. The next term we're going to use is bioleaching. So bioleaching. Now, bioleaching is another term to extract copper. And what we do is we mix the ore. So you'll get the powdered ore and you'll mix it with a leachate solution. So instead of having to do costly processes to try and purify it, you'll stick it with the bacteria. Now, the bacteria is just put in a pot. We put it simply, here's your bacteria here in the little grey parts, and here's your solution of copper sulfate. You then process to obtain the metal after the bacteria has taken it out of the ore-based slurry, okay, or solution. Okay, and then you take it out of this leachate solution through electrolysis or displacement of copper by adding scrap iron. So there's your electrolysis again. So between now and the next slide, maybe you could try and remember what those equations were for electrolysis again, try and write them down. So stop the video, try and write them down. Now, if you stop the video and then start it again, here are the answers. So what you've got here is you've got your leachate solution, really important, that's a mark-worthy point. You've got your electrolysis. Your electrolysis will have that happening, okay? So again, you've got the copper 2+, okay, and then again, you've got this oxygen being produced. We also have the copper sulfate. So if I go here and I say, right, okay, here is copper sulfate, added to the scrap iron. Okay, you make iron sulfate and copper, and there's your nice copper that you use to make all of your products. So really important, bioleaching, okay. Again, doesn't have to use the same amount of energy as normal conventional mining does, okay, and also doesn't take as long to do as phytomining does. So there's two clear points as well. But remember, you're going to have to remember this equation, and you're going to have to remember these as well.